Hi, and welcome to my first video in the Heat and Thermodynamics series. What I want to do in this video is get an intuition of heat and thermodynamics, specifically calorimetry. Calorimetry is the measurement or the science of heat. The science of heat. In our normal world, we perceive heat in both ways. Something can either be hot or cold. But that's not enough for physics and chemistry. What exactly does heat mean? What does it exactly mean to be hot or cold? Well, heat is simply a measurement of the average kinetic energy of a gas, solid, or liquid. So heat, often abbreviated as Q for energy, is the measurement. Let's make this neater. Is the measurement of average kinetic energy, of average, AVG for average, kinetic energy. And kinetic energy is the energy of motion. Let's take a look at an example that we should be very common with, or that should be very familiar with us. If we have a cup and we fill that up with water, let's draw our cup. And let's say we fill this up with water. And in this state, our water is a liquid, correct? And let's say that's at room temperature. So here's our water, and here's our cup, and we have this here. If we were to pour out the water and make it into an ice, like this, an ice cube, then from our intuition and basic knowledge of life, we know that this ice cube is colder than the liquid water. So this is colder. But how does this look on an atomic level? Well, the ice is obviously more organized than the water. We hit all of its molecules. If we say that each of these molecules is, or each of these dots is a molecule, all of these are very compact with one another. They're touching each other side by side. Correct? And this goes on all faces and in the inside of the cube and whatnot. So these molecules, they don't have much space to move around. They're shaking in place back and forth. So let's zoom in. We have two molecules like this, and each of the molecules are trying to move up, down, left, right, backwards, and forwards, but on each side they meet another molecule that's also doing the same. They're bumping into each other, but they don't have much space to move around. And since they don't move around, these have a low kinetic energy. Low kinetic energy, Ke for short. The molecules in the water, however, they're not as compact. They're fluid. They can slip past one another. They're not in this grid shape that we have right here. They're slightly more disorganized, but they're relatively organized compared to gases, plasma. So these guys, they have lots of movement. They can move whichever way they want. They'll rub into each other, but they're still, for the most part, they're still connected and interacting with one another. And we perceive this as a medium kinetic energy. Ke for kinetic energy. And our last state of matter that's important for our test is water vapor, correct? Let's say that we take this water in the glass right here and we vaporize it, and it's this gas now. And why gases are kind of interesting is because the molecules actually have very little interaction with one another. They're moving this way and that, and they rarely ever bump into each other if they ever do. If they do, then we have completely elastic collisions, meaning that our kinetic energy is conserved. And these guys have very high kinetic energy. High kinetic energy. Let's make that neater. Kinetic energy. And from our daily lives, we know that ice is colder than water, and water is colder than vapor. And we take a look, we can actually see correlations between kinetic energy and heat. When we have low kinetic energy, we're cold. When we have high kinetic energy, we're hot. This is below, the temperature of this is below or less, or is less than or equal to 0 degrees Celsius. And this temperature right here is greater than or equal to 100 degrees Celsius. So we can see that as our kinetic energy increases, the hotter we get. And the lower kinetic energy we have, the colder we get. Colder we get. So that's good and all, but what does this have to do with physics? This is just too easy to put on a test, correct? What we're now going to take a look at is heat transfers. Specifically, the amount and how heat is transferred from one object or another. Heat transfer. But if you remember from a past video, we said that heat is a measure of kinetic energy. So what's actually being transferred is not heat, but rather kinetic energy. When we put our hands on a piece of metal or something else that we perceive as cold, the energy from our hands is being transferred into the metal. Let's take a look at a really quick example. So we have a line right here that serves as a boundary, and let's say that we have molecules on this side that are very high kinetic energy. They're moving this way, that way, this way, and somewhat. And then we have another object on this one that's very compact, and the molecules are not very moving at all. They're relatively still, and they're stuck in this grid-like pattern. Actually, you can tell that this is a gas and this is a solid. But what's going to happen is when one of these molecules comes and hits this boundary, the molecules within the boundary are going to vibrate. And they're going to vibrate because the kinetic energy from this one is going to transfer into here. And when these ones vibrate, they're going to hit the molecules here, and these guys are going to vibrate. And soon enough, when enough kinetic energy from these guys is transferred into the barrier, and when enough kinetic energy is transferred into the solid is now going to become a liquid. The molecules are still relatively compact, but they're not as compact and we have more energy. So what's happening between our hand and metal system is that the kinetic energy from our hands is vibrating into the metal via kinetic energy. So our molecules are vibrating super fast, and they're going to hit the metal, and they're going to transfer their kinetic energy into the atoms within the metal. Okay. So what's important to note about heat transfers is that heat always transfers from hot to cold. Always. So it's going to transfer from high kinetic energy to low kinetic energy. But how much heat gets transferred is actually dependent on several properties. The first of which is going to be mass. The second is an intrinsic value called specific heat. The specific heat of any object, let's actually, heat. So the specific heat of any object is an intrinsic value that says the heat required, so the heat required to increase the temperature of 1 gram of any substance of temperature of 1 gram of any substance by 1 degree Celsius, or Fahrenheit, or Kelvins. So let's look at 2 examples, one water and one of gold. The specific heat of water of H2O is 4.186 joules per gram, or 1 calorie per gram as well. So to increase 1 gram of water by 1 degree Celsius, you're going to need 4.816 joules, or 1 calorie. For gold, on the other hand, the specific heat of gold is 0.129, that's on 9, 0.129 joules per gram. And to increase 1 gram of gold by 1 degree Celsius, you're going to need 0.129. As you can see, the specific heat of water is substantially higher than gold, and in fact, of most, if not all, objects. This is one of the reasons why water is very common to use as heat sinks, since it does not lose or gain heat very rapidly. Gold, on the other hand, is a metal, and you should know intuitively that it does gain and lose heat very quickly. So, what does this really mean for heat transfers? What we can say is that the amount of heat that is absorbed or lost on an object depends on the mass, as well as the specific heat of water, or of the subject. So the amount, let's do this in new color. Let's go for yellow or beigeish. So the amount, and instead of heat, I'm going to say energy. The amount of energy absorbed is directly proportional to the product of the mass of the object, of the substance, of the mass and the intrinsic specific heat, and the specific heat of the substance. And we could derive from this wording a formula. for specific heat. And this formula is called the specific heat formula. Very crazy, I know. And what we're going to say is that the heat added or absorbed Q is equal to the mass times the specific heat C times the change in temperature, generally in kelvins. So if we take a look at this equation, we can see that we're actually taking the change in temperature. Now, that simply means that the change in temperature just simply means the temperature final minus the temperature initial. And this could very well be negative, correct? This could either be positive if the temperature final is greater than the temperature initial, or it could be negative if the temperature initial is greater than the temperature final. But what does this spell for Q? If Q is negative, so if Q, the amount of energy added or absorbed, sorry, the same thing, either absorbed or released, if Q is negative, then our object indicates a decrease in temperature. So this indicates a decrease in temperature. And if Q is positive, this signifies an increase in temperature. And there are other things that we can pull out from this equation that I'm going to quickly explain once I erase all of this. If we have an object of the different masses, the smaller object picks up heat the fastest. We can show this through simple calculation. If we have water, if we have a bucket of water, so we have a bucket of water that holds 1 kg, and we have another bucket that holds much more water, let's say 3 kg. Those are two different colors, but that's fine. And we add in, let's say that they both start at 20 degrees Celsius, and they both go up to 40 degrees Celsius. So we know our change in temperature is 20, since final temperature, 40 degrees, minus initial temperature, 20 degrees, is equal to 20. And let's take a look at how much heat is added to both of them. So for our first object, or our first example of the 1 kg water, I'm going to say Q is equal to 1 times the specific heat, and let's just use, for a specific heat, let's use 1 gram per calorie. Or sorry, that's the wrong way around. That should be 1 calorie per gram. So if we 1 times 1 times the change in temperature, 20. So we know that 20 grams, or 20 calories were added to this piece of water right here. So 20 calories added. If we take a look at our second one, our mass is no longer 1, but instead our mass is 3 kg. So I'm going to 3 times our specific heat is still 1, and our change in temperature is still 20. And instead of 20 degrees, now we see that we have 60 calories that were added. And as you can see, that the masses of two different objects indicates how much energy is required to increase by the same amount of degrees. And in fact, in this case, we required exactly 3 times as much, so 3x. So the masses of the object that we're adding heat to is quite important. And finally, the last thing we need to note is that the specific heat of an object is also important. If an object has higher specific heat, that means it's going to require more energy to be increased by 1 degree Celsius. We see that through our water and gold analogy or example. Water's 4.186 joules per grams. Gold, if I remember correctly, is 0.129 joules per grams. Water obviously has a higher specific heat, so which means that it's going to take longer, or it's going to require more energy to heat up by the same amount of degrees that we want to heat up a gram of gold. If you have any questions, please comment down and I will try to get to you as soon as possible. And the last thing that we need to talk about in calorimetry for this SAT subject video is heat transformation and phase changes. While an object, let's take a look at our water again. So while an object, and in our case, water, transforms into a pool of water, while it's undergoing phase shift, it actually does not gain energy. So let's take a look at this graphically so we have a better understanding and intuition of what's actually happening. And what I mean by during a phase shift, there is no increase in temperature. So we have our y and x-axis here, y and x, and on our x-axis we're going to have energy input, and on the y-axis here we're going to have temperature. So temperature. And we're going to depict this process right here, the melting of ice into water. So at 0 degrees, water is still water. Let's actually say that our 0 degrees is somewhere else. So right here is below is negative. And while this is happening, and bang, we're suddenly at 0 degrees Celsius, right? And we know that when ice goes above 0 degrees, it's going to transform into water. A naive thing to see is that we just believe water is going to keep on increasing in temperature. But it's not. We know that from studies that while the ice transforms into water, it does not increase in temperature until it fully becomes ice. And how we're going to depict that is, as we input more energy, the temperature is going to be the same until 100% of ice becomes water. So 100% of ice becomes water. And once all of it's melted, then any increase in any further input of water is going to increase the temperature. Until, once again, the water is not going to become water vapor. That's my best drawing of water vapor. But until 100% of the water becomes vapor, we no longer increase in temperature until 100% is now water vapor, and any further increase or input of energy is going to increase our temperature. And what we have here in two places is an important definition called latent heat of transformation. Let's get a color we haven't used so far, green. What green do I want to use? Let's use this. So the latent heat of transformation. I got a little bit squeezed, and I have to squeeze a little over here. But essentially, what latent heat of transformation is. The latent heat of transformation is energy released or gained by a body during a phase transition. So it is the energy gained or absorbed by a body during a phase transition let's see the next line so we have a little bit more space. During a phase transition, or any time that there is no change in temperature. And there are two types of latent heat. Latent heat of vaporization and latent heat of boiling or fusion. So this part right here is the latent heat. I'm going to abbreviate latent heat as LH for right now so we have a little more space. As the LH of fusion. And this right here is the LH of vaporization. The latent heat of vaporization is the heat needed to transform liquid water into vapor, or transform vapor back into liquid water condensation. The latent heat of fusion is the amount of heat needed to transform ice into liquid water melting, or liquid water back into ice, which is freezing. Before we end this video, I want to define two terms that might be important in which you might see on the SAT physics test, not on the AP physics test, is sublimation and desublimation or deposition. So sublimation and deposition. Or sometimes known as desublimation. So sublimation is a process where a solid transforms immediately into a gas. And an example of this is dry ice. It is very hard to have liquid carbon. And the converse of this is deposition, where a gas transforms immediately into a solid. This happens when we have liquid water in sub-freezing temperatures that immediately turns into a solid ice. So liquid, that's not a Q. Liquid H2O becomes ice. Yay! And that wraps up our first video on calorimetry and heat and thermodynamics. If you have any questions, please put it down below in the comment section and I will get to you as soon as possible. Thank you so much and have a great, wonderful, beautiful day.